comparatively speaking. We are not getting into the nitty-gritties of C-13 because C-13 can be used in a lot of different ways for different kinds of information. It's really very fascinating, but we are not doing all of that. So, oh, thank you. Thank you so much, Mark. Appreciate it. Okay. So in H-NMR, which nucleus are we focusing on again?
Hydrogen.
So in carbon-13 NMR, which atom are we focusing on?
Carbon.
Carbon. Of course, it is the carbon-13 isotope that is NMR active, but that's fine. We're looking at carbons this time, not hydrogens this time. Can someone tell me what's the first feature of proton NMR spectrum that we study? That we look for? Number of signals, right?
Yeah.
Okay. What's the second? Integration. Third? Multiplicity. And fourth? Chemical shift. That's for proton. Does everybody remember that?
Yes.
Okay. Fourth is chemical shift. So let's start with the first. What does the number of signals tell us? Anybody? If there are 3 signals, what does that mean?
3 types of hydrogens.
So what would that mean here?
3 types of carbons.
Number of signals is number of different types of carbons.
Exactly. It's the same, decided exactly the same way as you decide for protons. This time though, you're focusing on C's. Everybody okay?
Mm-hmm.
Integration, what does that tell us? How many hydrogens, right?
Yes.
We do not do that in carbon. Because you're studying the smaller isotope, which is actually in nature not very abundant, its percent abundance is pretty low. The best way to do carbon-13s is gather, scan, and then gather again, build on the previous, gather again, build on the previous, and build and build and build thousands, not thousands, okay, I'm exaggerating, but you're basically gathering many scans and building the data on top of each other. So because of that, the point is that because of that, we lose integration information. We don't have that. We good, everybody?
Mm-hmm.
We don't have integration in C-13. What about multiplicity? What does that tell us in proton? Neighboring hydrogen.
Number of
right?
neighboring hydrogen.
In this case, multiplicity tells us not neighboring hydrogens, it tells us neighboring
Carbons.
Carbons. However, oh, actually not. And this guy in nature, you just understand this, you don't need to memorize it or use it or anything. This isotope in nature is less than 1%. So what is the likelihood that 2 adjacent carbons will be C-13 at the same time? Very low. So it is really not about multiplicity, it's not about coupling with other carbons, it is actually, coupling with its own hydrogens. However, at this level, whenever we do carbon-13 spectroscopy, we will actually turn this off. So we will not look at multiplicity in C-13. These are called decoupled spectra. We will turn coupling off. So we will only work with decoupled carbon NMR, meaning no coupling. So no multiplicity. Everything will be singlet. All carbon signals will be single lines because we will turn this off. We good, everybody?
Mm-hmm.
Can we turn it on? Yes, we can. And then you see, the only thing is the spectra become pretty crowded because there's so many hydrogens and stuff. The spectrum becomes really crowded and it's really not convenient, so it's better to turn it off. What does chemical shift tell us? Where the signal is, right?
Mm-hmm. Yes.
Okay, so let's look at carbon-13 and try and look at some common areas, regions where the signals will show up. I gave you a handout for the table for C-13 signals as well, right? Okay.
You also you also have C-13 NMR on this
Yes,
on this
absolutely,
table
I
here.
do, right, exactly. Now, please notice, what is the scale of proton? Goes from 0 to what?
0 to 14.
About-ish, right?
Yeah.
This goes from 0 to almost 230, 240, 200 and...
220.
Yeah, it can go anywhere. So different scale altogether. I'm trying to remember, around 120, maybe 118 even for that matter, to about 130. This is the region where all sp2 hybridized carbons will show up. So benzene, carbons. Now please remember, now we are looking at carbons, not hydrogens. We are focusing on Cs. Benzene carbons will show here, but also alkene carbons will also show in that same range. I would say 160 to the is where carbon double bonded to oxygens show up. And these are generally very small because they have no hydrogens on them. So they're very small. Sometimes they're hard to pick because they get lost in the noise in the baseline. So you gotta be careful about that signal. But they are over there. Ordinary sp3 hybridized carbons will show up 0 to about 20. This is where sp3 hybridized normal, ordinary, with no electronegative atom or group attached to it will show. Actually, could I change that, please? Sorry, because it depends on if it's quaternary. You can actually take it to about 40. Sorry about that. Around the same is also where a carbon, sp3 carbon, next to a C double bond O will show up. Around between 30 and 40, in that range, it will show up there. About 50-ish is where carbon or attached to a single bond oxygen will show up. These are the important areas. And then about 80-ish or so is where triple bond carbon will show up. sp hybridized carbon will show up. Okay, those are the important areas. Oh, they took it to 150 almost. Okay, I guess, sure, if it's too electronegative, it can go. Those are the general areas. Of course, the table has more values, but for us to, keep in mind the common areas of where to expect carbon-13 spectra to show.
With the carbon triple bond carbon, would that also be small because there's no hydrogen on
Yeah.
it?
Yes, absolutely. So as a general idea for C-13 spectroscopy, if a carbon has 3 hydrogens, it's bigger than if it has 2 hydrogens, it's smaller. If it has 1 hydrogen, it's even smaller. And if there are no hydrogens, it's smallest. So the signal is biggest and smallest. Yes, absolutely. The triple bond carbon will also be pretty small because it has no hydrogen on it. So that's also something we see. We good, everybody? Now here's a hint for carbon NMR. There is no integration. So how are you to tell how many carbons is a signal for, responsible for? The answer is you can't, because there is no integration. However, sometimes, let me just draw something. Of course, we'll see examples as well. Sometimes you're looking at a spectrum where one signal is yay big and the other is yay small. In those cases, we can make an educated estimation saying that because this signal is obviously so much bigger than that let's say this is for one carbon, then that must be for two carbons. It's an educated estimation we are making. You can't really measure anything here because there's no integration. So we are making an estimation that this signal, because it is obviously so much bigger than that guy, maybe this is double the number of carbons than this guy.
Can we say 3?
Generally go by 2. Because again, be open-minded. Maybe it is 3. So when you're working through the spectrum and you realize, no, it needs to be 3, it's an estimation we are starting with. Yes, sir.
So on the other scale, biggest to smallest, the carbons with hydrogens, that's like
Exactly. So let's say we see another signal which is this big. Now if you're comparing, can I just call it A, B, and C? So if you're comparing A and B, I don't think it's reasonable for us to say because A is bigger than B that this is more carbons than that. Can't. It's probably because this has more hydrogens on it, therefore it's bigger compared to this has fewer hydrogens on it, so it's smaller. But sometimes, as we will see in examples, that when the signal is obviously way bigger than others, that you can start with an estimation. Does that sound okay, everybody?
Mm-hmm.
So in carbon 13, we don't look at integration really, except for in a qualitative situation, in a qualitative sense. We don't look at multiplicity because there isn't any. Please take one and pass. And the only things that really matter, most of the times the only things that matter are number of signals. The rest, just take one and pass.
Thank you.
Mm-hmm.
I'm so interested. There's another experiment that your book is talking about called a depth experiment, DEPT. Depth experiment, we are not getting into depths and all. But basically, it's an experiment where NMR, it is NMR, that allows us to decide whether a carbon signal is sp2 or excuse me, I misspoke. Whether a carbon is CH3 or a CH2 or a CH or so on and so forth. It can actually help us decide that. So in the first spectrum that you see on the front page of this new handout, they have given us that information. They're telling us whether each of the carbon signals is CH3 or a CH2 or CH and so on and so forth. That comes from what is called the depth experiment. It's an NMR experiment, but we are not getting into it. But once again, let's start with IHD. What's the IHD? C5H11 Br. What's the IHD? Anybody? Did you get one? 0. Okay, so no pi bond, no ring. Now let's look at the signals. Oh, by the way, please notice that is CdCl3. What is CdCl3?
Deteriorated chloroform.
Okay, what is it being used as? For what purpose?
The solvent.
It's just a solvent. That's not part of your compound. In carbon, in proton NMR, CdCl3 shows up at around 7.24 ppms. In C-13 NMR, CdCl3 shows up around 80 as 3 lines actually. So that's solvent, ignore it. So how many total signals do you see here?
4
4
signals.
signals. Now, if I let's label them just so it's easier to say which is which. C and B, everybody okay? Now, do you see how A? Oh, sorry, Ken.
Carbon triple bonded to carbon is also 80. Will that show up as just one line, as a singlet?
Yes, they all show up as C.
Oh,
all carbons, because we are intentionally doing decoupled C13, so no carbons will have coupling.
Okay, and so if you see a 3, then it's the.
That's CDCl. And around 8, yes, exactly. Okay, so there are 4 signals here, A, B, C, D. Do you see how A is obviously, do you guys agree? A is visibly way bigger than any of the others.
Yes.
Yep.
So in those situations, we can make an educated estimation that maybe A is for twice as many carbons as each of those are for. So if I were to say that this is for 1 carbon, 1 carbon, 1 carbon, then I can say A is for
2 carbon.
equivalent carbons, 2 equivalent carbons over there. Everybody, does everybody understand that? So, therefore, we can say signal A is for 2 equivalent methyl groups, right?
Mhm.
Because
Okay, yeah.
A is for methyl,
Yes.
it says so. And then
Yep.
we have 1 CH, 1 CH2, 1 CH2, 2 different kinds of CH2. So have we used up all 5 carbons?
Yep.
Have we used up all 11 hydrogens? So that's 6
6 plus 2
hydrogens,
is
7, 8, 9,
Plus
10,
2 is
11.
10, plus 1
Agree?
is 11.
And of course, there's a BR. All we have to do again is take these pieces, put them together, come up with a structure. Does anybody have a suggestion? What can this be? Yeah?
I was gonna say an isopropyl.
Isopropyl what?
Isopropyl with the, and then an ethane on the end with a bromine on the thing.
I like that thing. Isopropyl and the. Do these compounds have names? These you can name. We know how to name these.
Duetero. Is that the?
Oh, like the full name?
Duet.
Yes, the full IUPAC name.
Oh, okay,
I think you're referring to this guy. Am I right?
Yeah, yeah,
Does it have a name?
yeah. Yeah.
What is the name?
What is that? It's, 1 bromo, 3 methyl
Butane.
butane, thank you. I never remember butane.
Perfect. Do you
One
all
bro-
agree with that?
1 bromo 3 methyl butane.
So where is
Thank you.
signal A? Which carbons are responsible for signal A?
Isopropyl.
Yeah.
This methyl and this methyl.
Mm-hmm.
Where is signal B?
The isopropyl.
That signal B.
Mm-hmm.
And C and D. Which one would you expect to be C and which one would you expect to be D?
It's close to
D
the
is the
bromo.
one next to the BR.
Sorry, could you say that again?
D is the one next to the BR.
D is the one next to the BR and therefore this is C.
Mm-hmm.
Is everybody okay?
Yeah.
That's it? That's all we are doing for carbon 13. Please go ahead, tell me what
Next
is
year.
the answer there for same. Everybody understand that? Does anyone have questions?
Mm-hmm.
So please notice for carbons, there is no integration, there is no multiplicity at this level. Okay? Same chemical formula but different C13 spectrum. IHD therefore is still 0. But now notice the patterns are different. The carbons are different. So go ahead, why don't you guys work with each other? Go ahead, talk to each other. And tell
3
me what
plus
could
2 is
this
5 plus
be
2
the
is
structure
7.
of that compound, the second one.
See, okay, yeah, no, I can't think of it. So,
Wouldn't it be the second one twice as bigger? So it would be times 2.
Yep. Mm-hmm.
So let me label these.
3 plus 3 is 6. Wait, there are 2 CH3s. 3 plus 3 is 6, plus 2 is 8, plus 3 is 11. Yep.
So, gosh, I suck.
Okay, so there are 11. 1, 2,
So how
3,
many
4,
oxygens
5.
did I
5
use?
carbons,
So,
11 hydrogens.
3,
So
4, 5.
It
Okay.
would-
Wait,
Got
wait.
it?
I
1.
think so.
What do you have?
it wouldn't be an isopropyl because there's no C.
I'm sorry.
Shouldn't that have 3 equivalent carbons?
5.
Oh,
I have 6
Am I, maybe I'm picturing it.
C's. Wait, would this count as C?
Shouldn't it
Right?
have?
Yeah,
shouldn't
it's
all
just
three of these
C,
methyls
no
be the
H.
same?
Yeah, so
Yes.
did I do this one right? Where I multiplied it by 2?
Notice there are two different kinds of methyls.
Yes.
But this we can assume are two of them, absolutely. But then there are two different kinds.
Yeah.
Two of the methyls are identical, but the third is completely different.
Yeah.
Yeah.
Yeah. What do you have?
No, I don't have anything.
Oh. Okay. Yeah. So we have to come up with two identical methyls, one separate methyl, and then a CH2 and a quaternary carbon. Notice there is a carbon with no hydrogens on it, a quaternary carbon right there.
I'm getting 6 carbons, which is
No, it can only have 5.
Yeah, I know.
Yeah.
1, 2, 3, 4, 5.
But when I multiplied this by 2, I got 6.
Well, yeah, I did too. There are 2 carbons here, so oh shoot, I wrote on the screen. Oh shoot.
We want to.
Thank you. 1, 2, 3,
Yes.
4, 5.
Yeah.
Oh, I counted this to the.
No, that's because it's quaternary. If it doesn't have hydrogens, it's going to be small.
And don't count the.
But I
and
also
don't count
counted
the
this
deuterium.
one.
That's CdCl3, which is the solvent.
Don't count the. Don't count the.
So I don't count
Don't
solvent.
count
Solvent
the
is not your compound. You dissolve
deuterated
your
chloroforms.
Oh,
So does
okay.
anybody have some suggestions?
Oh, I have 5 also.
Yeah.
The quaternary carbon is the central atom.
What would you call this compound? Eric, Carter, what would you call it?
This is CH3, CH3. So this would be
Yeah,
CH.
that's what I got.
Bromo
Oh, no.
111 bromo
Why do I start?
dimethyl
Wait. so
propane.
That would be CH3. Oh wait, look at this.
Yeah?
Yeah.
What do you have?
Okay, I've got you.
Give me the name.
Proper naming. Okay, hang on. 1, 2, 3.
Wait. Oh, there is no
Okay.
H.
Two
Oh yeah, wait.
2 bromo 2 methyl.
CH.
Okay, it's 2 bromo, 2 methyl.
And then this.
1, 2, 3, 4. It's,
Then this, the bromo would be on here. And then it would leave.
So it's not right? No.
I swapped the methyl and the bromo and got the same result.
Okay, you looked at the.
No, I'm just processing it in my head. I'm just trying to work it. Is that what you said?
Yeah, that's what I got.
Is that what everybody's getting?
Yep.
No.
After swapping the bromo and the
Bromo,
methyl.
2 methyl butane.
Yep.
So which one is, oh, I didn't write on there. Okay, so this is,
3, CH2, CH3. So we have how many
let's call this
CH3s? I
A,
have
B,
1,
C,
2,
D.
3.
Which carbon is A?
On the left.
On the left?
Yeah.
Are you sure?
Isn't it the
This is the methyl that's completely.
Oh, so it's on the right.
so that would be
Where
a
is
A
B?
B
B is on the
Those
right.
are the 2 equivalent methyls.
B would be
Where is C?
these.
Don't say branch. The methyl E, right?
Mm-hmm.
And where is D? That carbon.
Yeah.
Everybody okay?
The quaternary carbon is D.
Everybody okay?
Yes. It's
So
just
now
C.
we are focusing on
and-
carbons, guys, not
This is
hydrogens.
C. There's no
Go ahead
B
and
on it.
read
Oh,
what
I
is the
should've-
third one? Also the same chemical formula, but different spectrum because it's a different structure.
CH3, all other CH2. So
Yeah, so they're all
Yep.
CH2, right?
So what is this?
Is it 1 bromo butane?
1 bromobutane, are you sure butane? There are 5
There's
carbons.
5 carbons. You're right. We're not talking about the other one now. It's pentane. Yes, you're right. I know numbers.
Samita,
Yes.
there's a spike in the graph between the CH3 and the all other CH2 that is not labeled.
Where?
Yeah. 1 second.
That one.
No, it is. That's what they're implying. They're saying all these
Oh,
are CH2.
Okay, so that's a CH2.
Those are all CH2s.
Okay, so there are
There's
4
one-
CH2s.
Exactly, there are 4 CH2s and 1 CH3.
Okay.
So So the only way you can put those together is one bromopentane. Sounds okay, everybody?
Yep.
So that's all we are doing
CH2,
for
CH2,
C13. Can I ask
CH3.
if anyone has a question? Okay, let's look at the next one. What does this IR tell us? What is the significance of this IR signal at 1740? Oh, I missed it. Sorry. I totally missed it. Oh, can I do this one a bit later?
Sure.
Yeah.
I will. It's very interesting actually, but let's do this first. Can someone tell me what's the significance of this IR? It's a CW0. How it comes into play, of course, we have to figure it out. But yes, it's an IR telling us, oh, there's a CW0. What's the IHT, please? C5H8. Oh, what's the IHT?
4.
Are you sure?
Isn't it 2?
Sounds.
Yeah, it's 2. I got 2.
Everybody okay?
Yep.
Now guys, please hear me out. IHT is coming out to be 2. One of them is
What's
the
used?
double bond, right?
Yeah.
Yep.
What's the second IHT for?
Another pi bond?
Where do sp2 hybridized carbons show up? Where do sp2 hybridized carbons show up?
3,000 to 3,100 inverse centimeters.
No, we're talking about carbons in carbon NMR. Where do sp2 hybridized carbons show up? Do you
Yeah.
see anything in that range?
No.
So can we have another double bond?
No.
So therefore, if
It's a
one of
benzene.
the IHTs is C double bond O, what's the other
Benzyl.
IHT for? A ring. It's basically telling us that IHT of 2 because one of the IHTs is the C double bond O, and because there's nothing in this area, the other IHT has to be a ring. You guys with me?
Yeah.
So now we have to think of a structure that has one ring and of course that C double bond O. But how many carbon signals are you seeing in the spectrum? 5?
2.
No, sorry, my bad. No, sorry, I was counting the 5. My bad. Yeah. 3 signals.
A, B, and C.
Oh, free signals, okay.
TMS doesn't count because we add that. Solvent doesn't count because we add that. That's not part of your compound. So notice the carbon signals, guys.
1, 2.
There are 2 different kinds of CH2s and one C that is not attached to hydrogens. And what kind of carbons show around 220? Anything 160 or so above, 180 above?
C double bond O.
Right there. There is a C double bond O. That carbon is showing up here.
Mm-hmm.
So please go ahead. Let's be creative. Let's solve this puzzle. What's the structure of this molecule? C5H8O. It has one ring and a C double bond O and 2 different kinds of CH2s. That's it. Let's get creative. Yes.
It only has 5 carbons.
Did you multiply by 3 for this one? For A?
Okay, there are total 5 carbons, because I just can't shut up. There are total 5 there are total 5 carbons, right?
Yeah.
1 carbon is used up there,
Yes, yes.
right?
Yeah, that's
How many
this guy.
left?
4.
And how many signals do you see? So what does that say about these 4? Symmetry. Exactly. 2 of them have to be the same, the other 2 have to be the same. Right?
Mhm.
I can't do it.
1, 2, 3, 4, 5.
Yeah, I can't. So what is that? And a ring. Remember a ring also.
4.
Oh.
It's a cyclopen.
We have a ring.
I think it might be a cyclopen
And then we have CH2.
C5H8.
Well, this is CH2, CH2. How many CH2?
You all get cyclopentanone? a ketone with 5 carbon atoms. Perfect. Does everybody agree? So when you solve this,
4, 6, 8.
right?
Okay, there we
That'll
go.
give us 3 carbon signals. IHD is 2. Are we all on the right track? Or on the same track rather?
Yeah.
Same track, okay, cool. Okay, this one, the one we skipped, I have to give you a little background information for this to make sense because it's a reaction we will learn next quarter. We will talk about this chemical reaction itself. So, alkenes, what are alkenes again, anybody?
C double bond C.
So, how many IHD is a C double bond C? Now, alkenes react with, if there is 1 pi bond, it reacts with 1 hydrogen and you need a metal catalyst. What are they using here? Nickel, fine, who cares? And the hydrogen adds across the double bond. What happened to the IHD?
The
Where's
IHD
the IHD?
disappeared.
Gone, right? But only with a pi bond. This happens only with a pi bond. If there were 1 pi bond, how many H's added if there were 1 pi bond?
2 H's.
Agreed? What if there were 2 pi bonds, so such as an alkyne? How many pi bonds here? What's the IHD of an alkyne? 2.
2.
So it will add with 2 hydrogens, hydrogen molecules that is. What happens to the IHD? Wrong. But how many H's added? 2 of them. Why? Because there were 2 pi bonds. 2 H's added. Because there was 1 pi bond. 1 H added. Does that make sense? Now we're not getting into the details. We'll do that next quarter. But how does this apply here? Please go ahead. Tell me what's the IHD of C7H8. What's the IHD of the original, the actual compound C7H8? Did I hear 4? Are you sure? I don't know, I don't remember actually. Someone confirm, is it 4? Okay. What is the IHD of C7H12?
2.
So please notice, this only reacts only with the pi bonds. So think about this. If you started with 4 IHDs, how many disappeared?
2.
So what does that tell us?
2 pi bonds and 2 rings.
So that means there are 2 pi bonds and
2 rings.
the other 2 have to be rings. Exactly. When you say the total IHD is 4, which means those have to come from 2 pi bonds. Those are the ones that disappeared when it reacted with hydrogen. Those pi bond IHDs disappeared, but then the ring remains. Because hydrogen doesn't react with the ring, only the pi bond. Yes, Dash?
Would that be the same for a benzene?
Not quite, and again we'll explore that more next quarter, next and second and the third quarter. Benzene, even though it has pi bonds, it's really technically not an alkene because of the delocalization. So it reacts differently compared to alkene. So we'll do that more later. But with this clue that okay, 2 IHDs disappeared, which means those were 2 pi bonds, that means the remaining 2 IHDs are 2 rings. And then the chemical formula C7H8, and here is the carbon spectrum. How many signals are you seeing here? So let's go ahead, let's try and come up with a structure for C7H8 based on these clues. C7H8 has 2 rings, 2 pi bonds. And then in the carbon spectrum of C7H8, there is 1 CH,
F50.
1 CH2. And then what can you say about this CH, the tall? Probably 2 of them. At least start with 2. If we need to triple it, we can go from it later. Let's start with 2. So that means
1,
2 equivalent
2,
and then,
3, 4.
but then we have 7 total
Yeah,
carbons
we need
and
to do
8
that.
total. So what does that indicate? Oh, symmetry somewhere. There has to be a plane of symmetry so that things become equal. Go ahead, brainstorm. And
5
don't worry
H's.
if it looks
C7
weird,
plus 1 is 8.
because it's probably not weird at all. It's about becoming creative.
And then we know we have a ring. And we know we have a python. So C.
As long as we are accounting for the IHDs, we are accounting for the carbon signals. Let's see what we come up with.
2 rings, 2 pi bonds.
But there's no carbon. They all have hydrogen.
How did you do yours? Did you do it?
No, I didn't.
I'm confused.
Because the compound we're trying to figure out structure for is C7.
Oh, it's gonna be a benzo ring. So it's gonna
So we are coming up with the structure for C7H8. That's the question. And the clues are, because of the added data information, C7H8 has 2 rings, 2 pi bonds. It has 2 equivalent CHs, a different CH, and a CH2. How do we put all of this together?
2. This is 1. Wait, I want to do 3. How do I draw 3? So it's gonna be 1. Do you know how to draw? Wait, I know.
Wouldn't this CH be the same size as this one?
And please remember, the carbons don't have integration. So the size is short. That's an estimation of ours that CH is twice as many carbons as the others. But it's an estimation on our part.
I don't know what I'm drawing. 7. Then we have a pi bond.
So you're saying the one at 140 is those 2, right?
Yeah.
Those 4?
Yeah.
And then, because that's an sp2 carbon. That's it. Okay, let's see. Maybe that's also a clue, right? Those are sp2 hybridized carbons. Good point. I think. And then there's an sp3. Yeah. There's one more possible structure.
I like your
Guys, here's another clue
It's
that
bad.
But I like it.
we just saw.
It's
creative.
What kind of carbons show in this part of C13?
A double.
SP2 carbons.
So that also is a clue that, oh wow, we've got twice as many sp2 hybridized carbons compared to the sp3 hybridized carbons. A clue. If there's sp2 hybridized carbons, obviously because we need 2 pi bonds.
I don't know. Oh wait, that should be the bigger one. That should be the bigger one. This one should be the
That's
smaller one.
creative.
I think it might be.
I drew this. This is terrible. But it's great.
But it's gonna have an H. Wait.
Yeah, pi bond with a ring.
No, that's wrong. Because then
So what would we have to do? Like 12 H's and 7 C's? Or what?
We have the right for C7H8.
Yeah, no,
We're
have
doing the
4
first one.
IHD total.
We're doing this
But when
one.
you add the thing that
before, like are we doing this one?
Yeah, we're doing C7H8.
Yeah.
These ones. So we have to figure out 8
Like a structure. Like the thing is, I don't know.
8 H's.
shove them in both of them, or the other
And then we have to account the 4 2 rings. We're gonna have 2 rings and 2 pi bonds.
The one you wrote was C7H10.
Yeah. So it was bad.
2 rings.
1, 2, 3, 4, 5.
I think you're good.
The structure you wrote was C6H10,
Yeah, I know.
not C7.
How about like yours?
Where do you have yours? Can I see?
I erased it. It wasn't right.
I'm thinking if you just put a line, would that work? No. Yes. No, probably not.
Because we're trying to get 8 hydrogens and
We have
7.
5 pi bonds. That would be
Wait, did you
5
multiply by 5?
Look, how about these? Wait.
1, 2, 3, 4, 5, 6. We don't have a 7 though.
Oh, we would have 8.
Yeah. Wait, did you multiply by 5? This one?
Yeah.
Okay. Wait, I need. Oh, I hate this.
You love it, and you hate it.
Oh my god.
Me, yeah.
Right. We need to get 5. Okay, 5. How do you draw cyclo?
Cyclopentane.
There's no cyclohexane.
Yes, there is.
Ethane?
Pentane.
Ethane.
7. We don't do cyclo.
This
2
is
rings.
5.
You'd be using 2 more carbons, so there wouldn't be 2 rings.
This is hydrogen. This is 5.
I think we do cyclopropane. That's the only way you could have 2 rings. One, two, three, 4,
6, 7,
5, 6,
8.
7.
I need 3 more. Or wait. Wait, if I do.
Yeah, this is the exact same problem that I was thinking about.
There's 1 CH2.
This is C.
Okay. One of the structures I've seen a couple of you come up with
4, 5, 6,
is
7.
this,
Yeah, that's
Oh, see?
right? Here's your, first of all, it's
There's 2 pi
symmetrical.
bonds.
yeah.
Here's your CH2. Let me just label.
Oh yeah.
I think it's easier that way. Let's call this A.
But then there would be 2
Oh.
CH2. Oh.
No, because you have the.
So, where is A? Oh, this is B, right?
7, yeah.
This is A because sp3 hybridized CHs. And here are your C's. sp2 hybridized CHs. And look at the number of C's, 4 compared to 2. That's why the signal for C is so much bigger. 4 compared to 1, because that signal is so much bigger. There is actually one other possible structure, which is, this is correct. Absolutely, it fits the spectrum.
Did you do it?
It also fits
I did
this
that.
data, because if IHD is
What?
4, 2
Almost.
rings, 2 pi bonds, but then 2 of the pi bonds disappear, so IHD goes from 4 to 2. Perfect, it fits. Does anybody have another structure? Huh, what?
We're like 5 minutes over time.
No, like 2.
Oh, shoot, okay. Oh, I totally forgot. Okay. The other structure is actually a bicyclic ring. These are things we will actually start looking at.
That's cheating.
No, stop, listen, let me finish.
Sorry.
Where is I going?
Bicycle ring.
Yes, so here is ring and fused.
Oh.
Oh.
Sort of like an ornament.
That's
Like
okay, I get it.
it looks like an ornament.
It works, but this works too. 2 rings, 2 pi bonds. These are C's, that's your CH2, and these are the methynes. Okay, so here's the plan, guys. Tomorrow, of course, is lab, and everybody is going to come absolutely prepared to do what needs to be done, because this assignment was given 3 weeks ago, and I've only spoken to 3 people. Literally 3 people have come to run their procedure now. That's okay. You guys are there. For my assumption is everybody's going to come tomorrow. I'm going to open the door, and you'll get, because you know exactly what you're supposed to do. Right? Everybody? There's no lab quiz for this lab.
It's sort of like a lab final.
So, on Monday next week, when we come back from Thanksgiving break, we have a quiz, right? The last quiz of the course. So the quiz is going to cover NMR, proton, and carbon together. So we will actually, I will give you spectra that you will need to analyze and tell me what the structures are, so on and so forth. Cool. Well, I'll see you guys tomorrow. I was going to say have a great Thanksgiving, but no, I'm going to. Have a great day.
say.